I want to discuss a couple of issues that we still haven't addressed as far as one transistor DRAM cells are concerned. First is how the array as a whole looks like, how a one transistor DRAM array looks like. Second is delay, specifically the write cycle for DRAM, which is actually fairly simple, and the read cycle, which is not simple. It is actually a lot more complicated than any other kind of memory we have seen. And finally, we have to consider the issue of refresh of DRAM cells, which is really important. So first of all, this is how a DRAM array looks like. And the main thing about the DRAM array is the fact that we have to use sense amplifiers. We have to use differential sense amplifiers. These are usually latch-based amplifiers. We have discussed them before. And the thing about DRAMs is, one transistor DRAMs in specific, is that while sense amplifiers help speed up other kinds of memories, like SRAMs or ROMs, with DRAMs, with one transistor DRAMs, sense amplifiers are indispensable to reading. The reason is the cell itself is not capable of creating any kind of perceptible delta VBL. As we saw, it creates a very small delta on the bit line, specifically equal to VDD over 2 multiplied by CS over CS plus CBN. And this is a small delta V because CS is much smaller than CBN. And this is the maximum swing that the cell can create on the bit line. If you leave it forever, it's not going to do anything better than this. Whereas an SRAM cell, if left forever, can actually fully charge and discharge the bit line. It just would take such a long time because its resistance is high. So we have to use a differential sense amplifier here because that's the only way we can get a full swing out of a read operation. And so sense amplifiers by definition are differential. One transistor DRAM cells are single-ended. So how do we deal with this? In fact, all sense amplifiers are differential, and they are used with a lot of single-ended memories like ROMs and DRAMs. And the way to deal with this is to have 2 bit lines connected to each sense amplifier. And in each bit line, we will have a dummy cell at the end of the bit line. If we are reading from a cell in the upper bit line, we activate the dummy cell on the other side, and vice versa. The dummy cell might not contain anything actually. It's an empty cell. Because it's empty, that means that when we read from it, its bit line is not going to change, and it's going to remain at VDD over 2. Which allows us to develop a delta V, which allows us to use the sense amplifier properly. In terms of layout, the array is usually folded like this, so that it doesn't actually exist on either side of the sense amplifier. It exists on just one side. Now, the second issue I want to discuss is the write cycle. Specifically, what events happen when we perform a one transistor DRAM write, and what is the delay of each of these events. So a write operation is pretty simple. When we write, we do 3 things. First of all, we drive the value we want to write on the bit line. Then we enable the word line. And then we wait for the cell to store the value that we have driven. And so we can calculate these 3 delays pretty easily. Drive delay means that we are driving the bit line using a drive buffer. We will talk about this delay in detail in the next video, but this is basically the delay of an inverter chain, which we discussed in detail when we discussed logical effort. Word line delay can be calculated exactly the same way we did for ROM arrays, with one exception, which is word lines in DRAM cells are usually made using metal layers, which means that we can model them as a lumped capacitor, which actually makes calculating word line delay even easier. Finally, there's cell delay, which is basically the amount of time it takes for the transistor to move the correct value to the storage capacitor. So let's assume we are driving a ground through the through the access transistor into the storage capacitor. This is actually a single RC circuit, a single time constant circuit, and we can approximate its time constant as the resistance of the access transistor multiplied by the storage capacitor capacitance. And so all of these delays can be calculated pretty easily. Now, reading from a one transistor DRAM cell is a lot more complicated than writing. It involves a lot more steps. So let's think about what happens when we read. First of all, we have to pre-charge the bit line. This is not difficult. We can calculate pre-charge time pretty easily. It's more or less a single time constant circuit with the capacitance of the bit line and the resistance of the pre-charged transistor. You have to be careful though, because the bit line is now in the diffusion layer, which means that it has resistive components, and so perhaps you have to calculate an Elmore time constant for pre-charge time. Once we have pre-charged the bit line, we can actually enable the word line, and so we have to calculate a word line delay, which we already calculated, already talked about when discussing write delay. And again, these two components, pre-charge and word line delay, are pretty much present in all memory arrays. There's nothing strange happening here. Now, normally when we talk about read delay, the next thing that happens in an SRAM, for example, is cell delay. On the other hand here, the cell doesn't actually discharge or charge the bit line. What's going to happen is that we are going to have charge sharing. So the cell is going to charge share with the storage capacitor. So we're going to have charge sharing between the storage capacitor and the bit line capacitor. And this charge sharing time is actually pretty small, because the amount of swing we see due to charge sharing is really small. It's VDD over 2 multiplied by CS plus CBL. You can approximate this delay, charge sharing delay, is approximately 0.69 times the time constant of the access transistor multiplied by CS. But again, this delay is going to be responsible for a swing of 50% of the full swing, which is VDD over 2. We are not dealing with a swing of VDD over 2. We are dealing with a swing of delta V, which is very small, VDD over 2 multiplied by CS plus CBL. So maybe you should ratio this by delta V by VDD over 2. And in all cases, this delay, charge sharing delay, is going to be much smaller than all the other components of delay. Now, we can think of reading as done, more or less done. But again, reading from one transistor DRAM is not going to give us a full swing, so you won't be able to read properly unless we have also a sense amplifier delay. And in this case, use the delay expression from the latch-based sense amplifier in the sense amplifier video. So sense amplifier is going to take care of taking the charge sharing swing and maximizing it into a full swing. However, the thing about one transistor DRAMs is that once you read, you have destroyed the value stored in the cell. And so what you have to do is that you have to take the full swing values that you now produced from the sense amplifiers, and now these values are going to be present on the bit lines as produced from the sense amplifiers, and then they will be routed to drive buffers, perhaps the same drive buffers that are used for writing, and these drive buffers are going to drive these values on the bit line. And so we have to drive the values that come out of the sense amplifiers, and so you're going to have another T drive, similar to the T drive we calculated for writing. And once we have driven that, we have to allow for a T cell equal to exactly the T cell we calculated for write, meaning that this is a write operation, because every read has to be followed by a write in a one transistor DRAM. Now, it's pretty obvious why reading from a DRAM is slower than reading from an SRAM, just because of the fact that we depend on charge sharing, which means that we have destructive reads, which means that we have to write after every read. The last complication with DRAMs is the fact that they have severe signal integrity issues. The stored value is the charge on a capacitor, and that capacitor is relatively small. We will make every effort to make that capacitor as large as possible while preserving density, but it's going to be small at the end of the day in absolute terms, which means that a lot of different phenomena can affect the stored charge on this capacitor. Any phenomena that takes away or adds to this charge is going to change the stored value on the capacitor. One effect in particular that we know about is cosmic radiation, which tends to cause the value stored in DRAM cells to evaporate. Thus, DRAM cells will randomly just lose their data, which is why DRAM, one transistor DRAM cells, DRAM arrays are always used in conjunction with forward error correction, so that if there's a single bit error somewhere, we can actually correct this error. So we borrow forward error correction techniques from wireless communication and use them with this. But the other systematic reason that these cells will lose their charge is leakage. So if you look at any of the cells, this is a high impedance node, yes, but this cutoff transistor doesn't have infinite resistance. There's a lot of leakage charge flowing through this NMOS transistor, and with time, the stored value on the storage capacitor is going to evaporate. In fact, leakage is more of an issue for DRAM than it is for any other dynamic CMOS circuit. If you think about dynamic latches, registers, and random dynamic combinational logic, the thing they have going for them is that their inputs are updated every cycle. They pre-charge and evaluate every cycle, or their inputs change on every clock cycle for latches and registers, which is why you just need to make sure that the clock cycle is not too long, not long enough to allow leakage to have any impact, which it usually isn't. With memories, on the other hand, there's a danger that you might write something in memory and you won't need it for a very long time. It depends on the program, really. It depends on the game you're playing. It depends on the video you are. It depends on what's happening with the program and the operating system. But there is a conceivable scenario, a very common scenario, where you write something and you come back to it a few seconds later. And a few seconds later is enough for the stored value to actually evaporate using leakage, which is why DRAMs have to refresh all of their stored data regularly. They cannot leave their data alone. They have to go back and rewrite it regularly. So how much of an overhead does refresh actually cost? Now think about what refresh is. Refresh means that we read values from each of the cells and then we write them again, right? So that's all it means. We read the values from the cell and write them again. But notice that when we discussed a read cycle for one transistor DRAM, it always included a rewrite at the end of the cycle because of the destructive read. So all we have to do is just do a read operation, and that would be a refresh operation. Now, if you look at the array, when we read from cell 00, for example, we will also be reading from cell 01 and cell 02 because we have enabled word line 0, right? So when you enable a specific word line, you are going to read from all the cells in the word line. Because you are reading from all the cells in the word line, you might as well use the sense amplifiers and the drive buffers to rewrite to all of these cells. So you can do refresh on a row-by-row basis. You don't actually need to go and refresh on a cell-by-cell basis. You can refresh a whole row in a single read cycle. So we can refresh an entire row using one read operation. So the amount of time it takes to refresh one row is t-read, right? So how many rows are there in the array? Let's assume that we have m rows in the array. So we have m times T read operations, this is the total amount of time that we spend on refreshing. But how often do we need to do this refresh? How often does a row need to be refreshed? This depends on the amount of leakage that the row observes. So let's assume that a cell, the storage transistor, has a leakage current of I leak, for example. And so this would be the capacitive current, the current in the storage capacitor, which has the expression Cs times delta V over delta T. Now let's assume that we can tolerate a certain delta V, a certain loss in the stored voltage of delta V. For example, if we can tolerate VDD dropping down to 0.8 VDD, then delta V would be 0.2 VDD. In that case, the amount of time that can go between two refreshes is going to be Cs times delta V over I leak. Obviously, if you have a larger storage capacitor, you have to refresh less often because you have more charge on the capacitor, which takes more time to leak away. So this is the amount of time that can pass between two consecutive refreshes for a specific row. Now, this is the amount of time that passes between one row being refreshed and that specific row being refreshed again. But how often does the memory as a whole need to do refresh? So the memory as a whole needs to do refresh so that every row observes only a delta T between two refreshes. And therefore, the refresh rate is going to be delta T over M, where M is the number of rows. So it has to perform refreshes at a much faster rate because it has to do it so that row 0, for example, observes a time of delta T between two refreshes, which means it has to do it M times faster. Now, what's the overhead still? Like this is how often it has to do it, right? So that's the time duration between two refreshes, right? So T refresh is going to be delta T divided by M. But what's the overhead? During this whole time, for most of the time, it can be doing reading and writing normally. But for some time, it is wasting some time just to do a refresh. So what is that time? It's a read time because refreshing is equal to a read, right? We are just reading and writing again, which is equal to a read for a one transistor DRAM, which means that the overhead of refreshing is T read divided by T refresh, which is delta T over M. This is the overhead.